Hello students. Now let's do some exercises on optimization with two variable cases. For that I am taking problem number 5.10 from chapter number 5 of Edward Dowling's book. Here in question number A, z is given as a function of 3x square minus xy plus 2y square minus 4x minus 7y plus 12. And given this, we are asked to identify whether the function is at its relative maximum or minimum, concave or convex. But as you can see that this is a two variable case where we are getting x and y. So in that case, we need to differentiate z with respect to x once. So we are taking the first order partial derivative, and where we get 6x minus y minus 4, we set it equal to 0. And then if we work on it, we can write 6x minus y is equal to 4. Let's say this is the equation number 1. Similarly, we need to solve for zy, and if we take the first order partial derivative of zy, then we get a negative, then we get a, yes, negative x plus 4y, yes, 4y, and then a negative 7. Set it equal to 0. Then from here we can also write that a negative x plus 4y is equal to 7, and we can mark it as equation number 4. Okay, now let's work on this. So if I multiply my equation number 1 with 4, then I will get 24x minus 4y is equal to 16. And then I write down my equation number 2, which is minus x plus 4y is equal to 7. So from here we can see that this 4y and 4y thing crossed out. So we are left with 23x is equal to 23. Or in other words, x is equal to 1. And then if I plug in x is equal to 1 in equation number 2, then I get minus 1 plus 4y is equal to 7, or 4y is equal to 8. In that case, we get that y is equal to 2. So we have got two critical values, x and y. I'm sorry, let me refresh it again. Okay, so we have got two critical values, x and y, which are 1 and 2. Now let's say take the second order, let's look at the second order condition and take the second order derivative. So z of x, once differentiated, it was 6x minus y minus 4. If it is differentiated with respect to x again, we get a 6. This 6 is definitely greater than 0. Okay. Now similarly, in terms of zy, we get a negative x plus 4y minus 7. If we differentiate it twice with respect to y, we get minus, we get a, sorry, not a minus, we get a 4. Okay, we are differentiating it with respect to y again, and we are getting a 4, which is again greater than 0. So you see that the second order derivative here with respect to x and second order derivative here with respect to x both are actually positive values. Over here and over here, these are the positive values, so greater than 0. So what can we say? We can say that the function is at its relative minimum and convex, but we can only finalize this decision if the third condition is met. Now let's check for the third condition. The third condition says, the third condition says that if z of xx into z of yy is there, it has to be greater than z of xy square. Only if this condition is fulfilled, then we will take the decision from the second order derivatives, partial derivatives, that the function is at its relative minimum and convex. But let's first calculate. So we will not put this sign now. We will put it later. Okay, we will put this sign later. So just write z of xx into z of yy, and here we will write a z of xy square, and then let's plug in the values. So z of xx is simply 6, z of yy is simply 4, and z of xy. So we need to see the partial derivatives now. Okay, if we differentiate second order derivative, that means if we differentiate z of x, which was 6x minus y minus 4, if we differentiate it with respect to y now, we get a negative 1. Similarly, if we write down z of y here, z of y, which is equal to, the first order derivative is equal to minus x plus 4y minus 7, and now differentiate it with respect to x. What do we get? We get also negative 1. So according to Young's theorem, remember, the second order cross partial derivatives will be equal to each other, and while we are differentiating z of x with respect to y, we get minus 1. Then again, we differentiate z of y with respect to x, and we get a minus 1. So altogether, as the cross partial derivatives are equal to each other, so we can write that minus 1 square. So in this side, we have got 24. In this side, we have just got 1. Which one is greater? Definitely this one is greater. So that's how from bottom to top you put the sign, so that you put the correct sign over here. Okay, and see, the condition has matched. Z of xx into z of yy is greater than z of xy square. So the third condition is fulfilled or satisfied. As a result, we can now look back at second order condition, and here we can see that the z of xx is greater than 0 and z of yy is also greater than 0. So the function is basically at its relative, sorry, not maximum. The function is at its relative minimum and convex in shape. So this is, let me write again, this is convex in shape. So this was the first example. We get a case of relative minimum and convex. Now let's see whether we get something else or not. So in question number B, the function of xy is equal to 60x plus 34y minus 4xy minus 6x square minus 3y square plus 5. So this is a long equation. Again, we would like to solve for the necessary condition first. So we will differentiate it with respect to x. So we can also write it as f prime x, and we get 60 minus 4y minus 12x, set it equal to 0. Or we can write minus 4y minus 12x is equal to minus 60. Okay, this can be equation number 1. Then similarly, f prime y is simply equal to 34 minus 4x minus 6y. Again, remember, we are taking the partial derivatives. Okay, and if we rearrange it, we get minus 4 of x minus 6 of y is equal to a negative 34. Let's say this is equation number 4. Now, I have already shown you this solving the system of linear equations and identifying the critical value in the previous math. So I'll not be doing this calculation again. Just do it by yourself. What I can say is I can tell you the critical values over here. What are they? Okay, so x and y has come out to be 4 and 3. Try it by yourself. If you can do it, I will talk about it later again in the live sessions. So after doing that and after identifying the critical values, now it's time to focus on the second order derivative. So if the first order derivative is 60 minus 4y minus 12x, then from here we can see that the second, or not or, we can see that the second order derivative f of xx is equal to negative 12, which is less than 0. Similarly, f of y, we have got 34 minus 4x minus 6y. So f of y is simply negative 6, which is less than 0. Again, it altogether reminds us that as both the second order partial derivatives are less than 0 here and here, it represents that the function should be at relative max. It should be at its relative maximum, and then it will be in concave in shape. So this is a preliminary decision. All depends on what the third condition is telling us or showing us. So let's look at the third condition. Okay, according to third condition, we will do z of x, or here it is f, I'm sorry. So this is f, right? So we can write f of xx into f of y, whether it is greater than or less than f of x square. I'm not putting the sign here, but let me calculate the cross partial derivatives here. Actually, it's better when you are solving for the partial derivatives, direct partial derivatives, also solve for the cross partial derivative. Then you don't need to do it here again separately. But as I haven't done it, let me see what are the cross partial derivatives. So here f of x is 60 minus 4y minus 12x. No, I need to rewrite it. So here f of x is equal to 60 minus 4y minus 12x. So f of xy is simply equal to negative 4. Similarly, f of So, and this is, I'm performing the cross partial here. Okay, so here also you see f of y is equal to 34 minus 4x minus 6y. So we get f of y is simply equal to a negative 4. So the cross partial derivatives are equal to each other. With that, what can we write over here? We can write that the first order partial derivatives were negative 12 into negative 6, and here it is negative 4 square. Now let's calculate. This 4 square is simply, sorry, it is simply 16, and here it is a positive 72. Again, this one is greater, so we will be moving from below towards upwards. And the third condition, sorry, and the third condition is satisfied. If it is satisfied, then we will move towards the second order derivative, but second order partial derivative results again. And the second order condition shows that both the signs are negative. So f of xx is less than 12, minus 12, which is less than 0, and f of y is negative 6, which is again less than 0. As both of them are carrying same signs and they're less than 0, we can say that the function is at its relative maximum and it is concave in shape. So that's where this particular problem ends. Now let's see whether we get any particular problem of exception. Yes, there is one. So let's see. So this is question number C of the same math. We are doing maths number 5.10, and now I'm at question number C, where Z is simply equal to 48y minus 3x square minus 6xy minus 2y square plus 72x. Here, the first order derivative, if we take, we get 6x minus 6y plus 72, and rearrange it. So what you can do is negative 6x negative 6y is equal to negative this is not 172, this is just 72, sorry. Okay, so minus 6x minus 6, oh, here it is y again. Why I'm making so many mistakes? Okay, so this is 6x minus 6 y, which is equal to, I said, a negative 72. Suppose this is equation number 1. Similarly, if we solve for zy, we get minus 4y minus 6x plus 48 is equal to 0. We can rearrange it. Minus 4y minus 6x is equal to negative 48. Make it equation number 2. Now, I will not solve for it. Please do it by yourself. But you can get a critical value for x and y is equal to 0 and 12. Okay. Now, let's take the second order derivative. Okay, for that, we will write the first order derivative first, which is negative 6x minus 6y plus 72 is equal to 0. So z of x is here negative 6, which is less than 0. Z of y is minus 4y minus 6x plus 48. And if we take a z of yy, we get a negative 4, which is less than 0. So both the signs are less than 0, indicating towards a relative maximum point. However, need to check the third condition. What does the third condition says? Okay, let me undo it again, and here now this time I will check whether the cross partial derivatives are similar or not. So earlier I did z of xx. Now here I will do z of xy for the same equation, and I get a minus 6 here. Here in this one, already partial derivatives has been taken in terms of y. Now I will do the cross partial. So z of yx, and I see that it is simply if I take the cross partial derivative here, if I take the cross partial derivative here and differentiate it with respect to x again, yes, here also I get a negative 6. Okay, so the cross partial derivatives matches with each other, equal to each other, and it is negative 6. Okay, so now the third condition. Third condition says that z of xx into z of yy, I'm not giving the sign yet, it has to be greater than z of xy square, but let's see what do we get. So we have got a minus 6 here, we have got a minus 4 here, and we have got a minus 6. So we take a square of this thing, and that's how we get a positive 36 over here. And here we get a positive 24. But the thing is, 36 is greater than 24. So that's how the sign goes on. Now, the third condition says z of xx into z of yy has to be greater than z of xy square. But what do we get here? A less than sign. Is the third condition satisfied? No, not satisfied. Okay, if not satisfied, then it has already fallen under the exception concept. What does the exception says? Exception says if the third order condition is not satisfied, even then we will go back to the second order condition and we will check the signs again. If z of xx and z of xy, they are carrying same signs, then we would say that the function is at its inflection point. Let me write. The function is at its inflection point. Okay. However, if it is carrying different signs, that z of x, y is, sorry, here also I made a mistake. It should be z of yy. Please correct yourself. Okay, now here, if I see that z of xx is carrying a positive sign and z of yy is carrying a negative sign, that means they are not carrying same signs, rather they're carrying opposite signs. So then the function is at a saddle point. I have discussed this very clearly in the earlier PowerPoint slides, but even then I felt it important to discuss a little bit. Now, let's see. So in the third condition, in the second condition then. Second order condition shows that z of xx is negative 6, z of yy is negative 4. Both are less than 0, carrying same signs. So what is our decision? As the third condition has not matched, but the second order condition is having same signs, that means the function is at its inflection point. The function is at its inflection point. Okay. So this is the result for this math. Let's do another and we will finish the video here. So it is question number D. F of x, y is 5 of x square minus 5 of x square minus 3 of y square minus 30x plus 4y plus 4xy. So we get f of x, which is the first order derivative, 10x plus 4y minus 30, set it equal to 0. So we get 10x plus 4y is equal to 30, equation number 1. Then we get f of y is equal to minus 6. Yes, we get minus 6y plus 4x minus 30 minus 30, which is equal to 0, or minus 6y plus 4x is equal to 30. This is equation number 2. And what are the critical values here? We get the critical values are x, y, which is 2 and 2.5. Okay, so these are the two critical values. X and y are 2 and 2.5. Okay, now let's take the second order derivative. So first order derivative f of x is 10x plus 4y minus 30. So f of xx is 10 greater than 0. F of y is negative 6y plus 4x minus 30. So f of yy is negative 6, which is less than 0. Let's see the cross partials here. Here the cross partial is f of yes, again here the cross partial is f of x y is equal to 4, and here the cross partial is f of yx is equal to 4. So the cross partial derivatives are equal to each other and holds the Young's theorem. But we need to check the third condition now. We have already observed that the two conditions, the two signs were different for the second order partial derivatives. First one was positive and the second one was a negative one. First one was a positive 10, second one was a negative 6. Now all depends on the third condition. So third condition says f of xx into f of yy, and here f of xy square, we want that this sign is greater than, in that case third condition will be satisfied. But let's see what happens. So here it is 10, and here it is a negative 6, and here the cross partials are 4 squares, so we get 16 over here, and we get a negative 60 over here. Which one is less? Definitely a negative 60 or less. So again we got the opposite sign. So the third condition is not satisfied. Okay, not satisfied. So then we go back to the second order condition and check the signs. So the second order condition shows, we have already seen that before, that f of xx is a is 10 and a positive value, whereas f of xy is negative 6 less than 0, a negative value. The third condition has not satisfied, and the second order partial derivatives are carrying opposite signs, representing that the function is at its saddle point. So this is another exception. With that, I am finishing this particular video. In the next class, probably in next week, I will show you the optimization with multivariable case, and we will also cover constraint optimization. Till then, please go through these examples well, try to grasp the concepts and also the economic applications and mathematical problems, whatever I have shown you, and come up with problems in the live session so that we can discuss about that if you really have any confusion. So we can end here. Thank you so much for watching this video.